Hi, and welcome to my presentation. My name is Ross, and today I'm going to be introducing you to my dissertation project, which is titled Seismic Interpretation of the UK Central North Sea. The project aims to assess whether or not there are geological storage possibilities for carbon dioxide or hydrogen in this area. Now, ever since the discovery of the Groningen gas field in the Netherlands in 1959, the North Sea has been an epicenter for research and development in the pursuit of hydrocarbons. Since then, the geology of the North Sea has been extensively studied, meaning that there is now a vast amount of geological, borehole, and seismic information available. As future hydrocarbon production decreases in the North Sea, attentions are turning to alternative uses for the geology that has already proven itself useful for storing liquids and gases for millions of years. Carbon capture and storage is a technology with enormous potential, but can only be realized with the identification of suitable and sufficient geological storage. Similarly, the use of hydrogen as a temporary form of energy storage for intermittent energy producers, such as wind and solar, requires geological storage, which could be provided by the North Sea. While CCS technologies are arguably more advanced than hydrogen storage, CCS has been greatly underutilized and development has been slow, consistently getting only around 5% of global annual clean energy investments. An investigation into the storage potential in the central North Sea region through seismic and geological interpretation would be useful in the development of a low-carbon energy mix in the UK, and this research project will seek to do this. Now I'll just briefly touch on a little bit of background to the technology to make sure that everybody listening is on the same page. CCS is a technology that enables either active drawdown of CO2 from the atmosphere through large fans that suck in and extract the CO2, or the direct capture of emissions from source. The figure on the left is a theoretical diagram of how carbon capture and storage would work. Here, we can see hydrocarbons being extracted from an offshore field and onshore mining, which in this example is for coal. These products are then transported to a power station and combusted to produce energy. At this stage, a CO2 capture plant will separate the CO2 from the emissions of the power plant. Next, the CO2 is piped off to an offshore rig, which would sit atop a pipeline into deep geological storage reservoir, where it will hopefully remain untouched by humans ever again. The type of reservoirs that can be used for storage include saline aquifers, depleted hydrocarbon fields, coal beds, and salt caverns. Additionally, the CO2 doesn't have to be collected from an emission source like a power plant. Huge fans can be constructed to just suck in huge volumes of air and extract the CO2 from it. Either way, it still results in a net drawdown of CO2. Likewise, the figure on the right here shows the storage of hydrogen, which operates on a similar storage principle. Here, hydrogen is produced from water during times of energy surplus. This could be done at an offshore site next to the wind farm or next to the storage site. The hydrogen would then be injected into a geological reservoir for storage. During times of high energy demand, this stored hydrogen can be extracted from the reservoir on demand and combusted at a power plant to produce clean energy. Essentially, it's a huge battery. So, why is this important? Well, global atmospheric CO2 concentrations have reached levels where active removal of CO2 from the atmosphere is now going to be essential in order that the net zero emission goals, which were outlined in the Paris Agreement of the United Nations, can be met. Additionally, it is simply unreasonable to immediately halt the use of fossil fuel in favour of fully renewable sources, since the capacity is just not there yet. Consequently, CCS provides a way for fossil fuel producers to continue to combust to provide an energy source whilst limiting the amount of carbon that is emitted to the atmosphere from them. Likewise, other active emitters, like combustion engine vehicles, will still be in use for at least a couple of decades to varying extents. and active CCS would help mitigate the impact of this, whilst a transition to fully electric vehicles take place. The technology is more or less ready to go, but more storage sites would facilitate scaling up of the infrastructure and actually make it a reality on a large scale. Similarly, hydrogen will be a great energy storage solution and could be integral to the future UK energy grid, especially when you consider that electricity demand is predicted to increase significantly as fossil fuels are phased out, as a lot of that energy will be replaced by electricity. The ability to store vast amounts of energy from intermittent producers is paramount, and this technology can do this. So, critically, more storage sites are needed to facilitate this when the technology is eventually ready to be put into practice. Finally, the central North Sea would be an ideal geographical location for these types of installations. With a fairly central location in the UK, close access to the densely populated parts of the country, if a suitable storage reservoir could be identified in this area, it could be very favourable. Minimising the distances that people and resources have to travel to reach sites saves time and money, which help make infrastructure projects like these more viable. Unlike the northern North Sea, which is far away from any densely populated area, pipelines are very expensive, and making them as short as possible can only be an advantage. This study seeks to further the understanding of the central North Sea geology. Additionally, it aims to identify whether or not there is potential for CO2 or hydrogen storage. Consequently, my research questions are to 1. Correlate the stratigraphic and structural geology of the research area. 2. Interpret the geology to constrain the depositional environments. 3. Identify potential suitable storage reservoirs for CO2 and or hydrogen. And finally, 4. To estimate potential storage volumes in any identified reservoirs. Once all of these research questions are brought together, they should give a well-rounded answer to the title of the project. So, how will all of this be achieved? Well, I'll be using seismic data that has been made available to me. The figure on the right shows the spatial extent of available seismic data covering the study area. For this data, I'll be using Petrel, a modelling software, which was provided to the university by Schlumberger. I'll also be using borehole data from the study area. I'm not currently fully aware of the extent of this data that I'll be able to get, but this is something that I'm currently looking into. Finally, the North Sea is an area that has been studied in great detail, and as such, there is a lot of literature available. So I'll be using as much of this as I can to help inform my analysis of the area. Critically, all of these sources are available to me online and as such are COVID-proof. It's unfortunate that they need to be COVID-proof, and it would be great to be able to get out and find a way to generate some original data or even go look at some rocks in some capacity. But you can only do the best with what you've got. So my methods for this study are fairly simple. I've divided it into 3 stages. Stage 1 will be dedicated to data acquisition and management. Stage 2 will be dedicated to data analysis and understanding. And stage 3 will be the write-up. There will be, of course, some overlap in these stages, but this is broadly how I intend on managing my time. I hope that in my study I'm able to come up with something that is useful and of some value to the industry of deep geological storage. Ultimately, I hope to prove or disprove the potential for CO2 or hydrogen storage capabilities in the central North Sea, at least as much as I can with the limited data I'll have access to and with the restrictions of the pandemic. If my answer is yes, then my work could serve as a benchmark for further exploratory work in this area, narrowing down areas of interest and maybe even providing rough estimates of potential storage capacities. If no, then the area can be removed from further consideration and no more valuable time needs to be spent investigating it for these purposes. So, either way, the results will be useful and something will be learnt from it. Finally, it is important to remember that the development of this industry and these technologies is exciting. We are hopefully witnessing the beginning of a new era for UK innovation in massive industry in the North Sea. Scientists and engineers have the opportunity to really advance these technologies and help lead the way for other countries. So, to be a part of that with this research, albeit a small part, is exciting to me, and I hope it is to you. I hope that you found this interesting. I certainly do, and I'm sure there will be many hours ahead for me working my way through this study, but hopefully in the end it will have been interesting and useful. I hope in the future to see more of these, and I also hope to see more of these, except being used to pump things into the ground instead of out of it. And I hope my research can play a small role in helping preserve this for future generations. So, thank you for listening to my presentation. And here are the references that I used throughout the presentation for the figures and my bibliography. Thank you.